So now I can do what?
Plug into
Plug it in. So now I know what my inputs are. I can go ahead and input them. So what's that look like now? Like we can simplify that a little bit. What does that look like?
So 1 plus 3i over n squared.
Yeah, 1 plus 3i over n squared to start with. Minus 4.
1 plus 3i over n.
Plus 2. I just took the function and I replaced x with the inputs that I want to use. The inputs look gross because they're based on things I don't know yet. I don't know what n is yet. So of course it's going to look a little gross. So simplify this a little bit. You can FOIL this without actually writing all the steps down, right? 1 times 1 is 1. 3i over n, 3i over n, so it's going to be plus 6i over n. This times itself.
9i squared over n squared.
Good. Minus 4 minus 12i over n plus 2.
So, negative 4.
Now just put your stuff together, right? Now it's less easy to see the parts because we've started to simplify it. It shouldn't look familiar at all anymore. So now we get 1 plus 2 is 3 minus 4 is negative 1. 6i minus 12i is negative 6i. Plus 9i squared over n squared. Let me stop there for a second. And again, the thing that's driving this whole thing is I know that the form of what I need to evaluate is this. So what do I need for this to be done? I need to know what delta x is. Check. I need to know what f of xi is. Check. All right, so now I can just plug it in. So what's this thing look like now? Go ahead and try to rewrite this here. Not there. Don't everybody come up here. We're trying to rewrite. Put everything in there in the right place. I'll stand here and hope. Alright, let me catch up to you here. Let's see. Size this business here. Delta x. Here's kind of like, there's a lot of mistakes that happen, but this happens very often as people will do this to themselves. Oh, that's so evil. So evil. Because then if you bring this in, all your i's become a larger power, so then the formula you use for your sum of I squared, is the wrong one. You guys kind of see what I'm doing? Don't do that to yourself. Always go back to exactly how you define delta x. It's just poor little old 3 over n. That's all it is. Maybe. So again, I would make that mistake. Alright. So let's see, let's bring this through. What do we get? We get 27i squared over n squared minus 18i over n cubed, n cubed, n squared minus 3 over n. So you just multiply 3 over n by each of these. So all the n's should go up by a power. I's go up by, no, I stay the same, and the coefficients go by 3. Cool.
So then just do separate?
Now you're trying to pull all the shit out of the way that's not I. Because I know what sum of I is. I know what sum of I squared is. I'll give you those too. I'm not going to make you memorize those. So these guys here, I will give you these. Right? You don't have to memorize them. Because I always forget this one. These two are easy for me to remember, but this one I always forget, so I'm going to just give them all to you. So like this first guy, I want to see who remembers. So here's the limit. The limit's just sitting out there waiting.
Did you take out? Even another 27 and
Yeah, I can take 27
n cubed.
and n cubed out. Why can't I take I squared out?
Because there's no way.
You
They
just
all don't have some.
No. So I'm not taking a GCF out. Let me make sure. I'm gonna do the sum of this minus the sum of this minus the sum of this. So I got 3 sums. You with me? If let me make sure you guys are really with me. All right. We're gonna do the same thing we did the other day. So can you see how for every I, this is a number, this is a number, this is a number. So how many of these do I have total? N of them, right? So couldn't I add all N of these up first, and then add these up and subtract it from what I got here, and then add these up and subtract it from what I got there? So what I'm saying is if I had to add 4 plus 8 plus 7 plus 6 plus 2 plus 3 plus 10 plus 10 plus 30, blah, blah, blah. I don't have to do 4 plus 8 is 12. Plus 7, no, I can do 4 and 6 and 10, 8 and 2 and 10, 7 and 3 and 10, and 30, and then add those all together, right? Can't I add parts of a complete summation problem any order I freaking want to, because it's all just addition? So, to make sure you really understand, I can rewrite this as add all these up, and then subtract the sum of all these, the sum of all figures, and then subtract the sum of all these. So it looks like, this is not true, but it looks like this distributed. When it looks like an operator can distribute, we call that a linear operator. This is important for right now. If you go to DiffyQ, it's going to rule your life for a little bit, but right now, who cares? But what I really want you to understand, this is a sum of a bunch of shit. Who cares what order I add them up in? That's fundamentally what I just did. So now I can attack. I can attack this sum. I can take stuff out. And I really need this to make sense. Anything that this considers to be a variable cannot come out, because then it can't let the variable do what it needs it to do. What's it need I to do? It needs I to be 1 and then 2 and then 3. What does it think n is? It thinks n is a constant, right? And it is. It's a constant. It's just something I don't know. It's a constant. So 27 is a constant, and cubed is a constant. I can GCF those bad boys out of that big old sum. That's all I'm doing. I can't take this out because it changes. It's not the same in every term. At first it's 1, and then it's 2 squared, and then it's 3 squared. So I'm going to factor out my GCF. That's all I'm doing here now, right? My algebra students would freak out as hell, but you guys can maybe hopefully see that's all I'm doing is taking a GCF out. So let's see, the first little dude becomes 27. Ooh, yeah. Where do you go? I squared. You take a second and write the other 2. I'm desperately trying to force some of you guys to be a little nicer to yourself and me and to your future teacher. Don't lose this dude. But do you see how I kind of factored it out of everybody? I've got it. It's there. And now I can just focus on all the sums inside. Yes?
with 3n just constant.
We're, sorry?
3n.
Yeah, officially you can take like a 3. Yeah, 3 over n out. Yeah, exactly. So then it's the sum of 1. If I add 1 up n times, that's this rule up there. But you know you're going to get n, right? Does that make sense? If I add 1 up 8 times, what do I get? 8. So if I add 1 up n times, what do I get? N. That's what that rule says. If I add 2 up 4 times, don't I get 8? So if I add 2 up n times, don't I get 2n? That's what that rule, that first one says. Sum a constant up, you're going to get that thing times n. Definition of multiplication. Let's see. This guy can be written as 18 over n squared, sum of I. And then minus 3 over n, sum of 1. So now this, and this we have rules for.
third. N plus 1 to n plus 1 over 6.
Yeah, do it again for me. I always forget that one.
N plus 1 multiplied to n plus 1 over 6.
That one? Yeah, okay. And then minus 18 over n squared.
N plus 1 over 2.
It should be n times n plus 1, yeah.
So there is also n.
There's an n here, right?
Yeah.
Okay, thank you. Alright, how are we doing so far? Again, I'm just using these rules here. Once I get it all stripped down to just the i's, strip everything away except the i's. It's grisly. Then I can replace those with what they actually are. And don't forget, we looked at a concrete example of this becoming this. Whatever n is, if I add, add up the squares up to that number, I'm going to get this. That's what I get. We did an example of that. So don't forget that connection. That's just the concrete of what the hell that becomes. So this becomes what? Sum 1 up n times, and you get n. So look what happens. Right? So that last one, that limit's easy. Look what happens everywhere else. What's the power up there? What's the overall power? Third power. What would the first term be?
2n cubed.
2n cubed. So what's the limit as n goes to infinity of 2n cubed plus crap over n cubed? 2. Let that be easy. That's pre-calc shit, right? If the degrees are equal, then it's the ratio of the coefficients. So what's the coefficient of the highest degree term up here? 2. It would be 2. And that guy's only got one term, so it's hard to see. It's just 1, right? And you see what happens every single term. That degree is the same as that degree. That's kind of like the equivalent of when we were doing the limit definition derivatives. Didn't the h's always cancel? Every function we did, do you guys remember back that far? Limit as h goes to 0. There was an h on the bottom. Damn you. But then you did something on top and bam, they all canceled. That's the equivalent of that. The degrees on the end will always be equal, so you can always replace it with a number.
So it's like a test. Like if it doesn't work out like that, then you can see that you don't.
I gotta be careful when I say always. If somewhere on the interval you're going over, the function is infinite, it might, it's going to represent that in a way possibly. It depends on what the function looks like. Yeah, but most of the time they have a nice function and it's defined over the interval. This is always going to happen. I can say that. Nice, continuous function, defined over this interval. This kind of thing will always happen. So then what's this limit here? 1. And of course that's gone. Who cares? So what do I have left over?
54.
Yeah, 54 over
9.
6, I like it, which is 9. Good. Minus
9.
9. Minus 3.
So it's negative 3.
So it looks like you get negative 3. Yeah. Alright. So how did I show you how to check this real quick? Did I show you? I did show you. So on your calculator, let's try this again real quick. You keep saying real quick, Jeff. I don't think you know what that means. Oh, man. Oh, I'll tell you what, before I forget, I'm going to give you guys the answer key. Tomorrow we're going to do number 5 as this is in class. I just didn't want to do a third page.
How did you
So which one?
cancel that stuff out?
So this one I canceled out completely, right?
Yeah.
These are because I'm taking a limit. I actually did the limit now. Now that I got everything in terms of n, I can let n go to infinity. That's not HSN.
Okay, so the n's go away.
So here, this is pre-calc. This would be 2n cubed plus stuff over n cubed, so that limit is 2, because they're the same degree. And like Robbie and I were just talking about, if the function's nice and your interval is where it's defined over it, this will always happen. If that's n to the 5th, that's going to be n to the 5th, so that you can do the ratio of the coefficients. Where'd I end up, you guys?
Yeah, I hope
Nifty. Going into my shit. Before I pass it out, it's my shit.
Grab happy.
Going into my pile of stuff.
Alright.
Oh, that's right. I was like, what was I in the middle of? So, okay. Delayed reaction. Two things I want to show you right now that are kind of cool. These are leftover Newton's method stuff. So, if we go to y equals, and we put in there, where to go? Oh, shikes. What was it? X squared minus 4x plus 2. Everybody, once you put it in there, hit zoom 6 so we all have the exact same picture.
X squared minus 4x plus 2.
Yeah. And I'm trying to integrate from 1 to 4. So here's our first. The integral from about 1 to 3 would come out how? How? Negative, because all my functions are below. So it's like negative area. So if we just do, let's just do 1 to 3 first. So if I do calc integral, this last dude, if I just go from 1 to 3, it's negative, right? And that kind of explains why the answer, now what do you think is going to happen when I add in from 3 to 4? That's probably going to be 1/3. It's going to cancel out that 0.333. So we got negative 3, didn't we? So I don't know if anybody was freaked out that we got a negative answer here. But that just meant that most of that function was below the x-axis. It's a negative area. So now let's do the integral from, go second trace to get to calc 7 for integral. From 1 to 4, negative 3. Cool. You guys get the same thing, or what's up? You guys all right?
Yeah, negative 3.
Yeah, it kicks ass. Isn't that nice?
How did you know it was? Oh, because the interval at the given. Okay.
So remember, the nice thing with this symbol they chose is it has an actual, bottom and top, and it's a nice representation of going from this to this, A to B. So those numbers they put outside the S, the big ass S, represent A to B, represent the interval over which I am interested in the area.
So what was the purpose of you checking the interval of 1 to 3? Why?
Oh, just to show you that was purely negative. I mean, and then, because that was all under the x-axis, right? So that came out to be negative 3 1/3. So the fact that ours came out to be negative 3 made sense, because when I added that little bit of positive area in, it took it back to negative 3. So why did I actually do it? I don't know. Just to show. It was purely negative there. Yeah. I like it. Okay. One quick little question. If I would have done this, everything is the same except the question would have said this. What would the answer have been?
Positive 3?
Positive 3. I love it. Because now, like, the main thing that changes is my width becomes negative. Yeah, so the integral from A to B of some function is equal to the negative integral from B to A of that function. Which is how you take care of if you don't want the area to be negative, if you actually want to add on that distance. So I went over here, so I went, and then I kind of came back, and I still went that freaking distance. It shouldn't subtract off. I want to add that. You just change the limit, you just turn them around, and then your interval is going to come out positive. It won't be a negative area. That's kind of like in our future, but... Okay.
So, like, with the sum of, like, the sine function from 0 to pi, would that be 0?
I love it. So there's a lot of functions you already know. You can pick out limits. That's what I don't think I've said that word yet. The limits is what I call the A to B. Those are my limits. And it's a little weird to say that word because it doesn't immediately mean what it's supposed to mean. But that's the limits of the interval. The limits of the interval. Several functions I can tell when it cancels itself out. And sine and cosine, of course, They're eternally canceling each other, themselves out, right? I like it. Kick ass. Okay. I'm just so happy that I think I'm coherent. Am I? You're like, as much as always, Jeff. It's just not that much. All right, I'm trying to remember if there's anything else. I mean, I think that's all I wanted to tell you today. There are some rules about basically what is, one last thing and then I'll let you go.
Yes.
I got you all excited. Gotta remember, I'm like Columbo. One more thing. One more thing. Let's see if I can. Here's kind of a neat thing. So say something weird happens, get out of there, at a point C in the middle. I want to get this total area here, right? I want to get this total area here. Are you with me? So this is officially what I want to have happen. So, and what does this represent? But less specifically, more generally.
The infinite sum?
The area.
Sum. It represents a sum. So what makes sense then? At C, what is bad about the function? A couple things. It's not continuous and it's not differentiable, right? Both of those suck. So what I can do is it cool from A to C?
Yeah.
It's coherent. From A to C, it's completely coherent, and from C to B, it's completely fine, isn't it? So if I just take the sum and go, okay, take the sum from A to C, and then add that to the sum from C to B, that is, I can do that legally. This I cannot do legally directly. I have to break it up so my function is continuous, differentiable on that interval. Differentiable not as important right now. Whew. You guys kind of see that? And so the same thing, if I had a negative piece I didn't want, I could do this the same way, except now, if I have a negative piece that I want to be positive, like here, I want to get this total area. I don't want this to be negative. I want to get the total area, right? I can break this up. I just have to, I can switch those or I can minus it, either way, right? But I just switch it to make it not a negative area anymore. Okay. So those kind of rules are in section 5.2, these integral simplification rules. Breaking an integral up across a point in the middle. It's an infinite sum, so if I just add up two parts of it, of course, you get the whole thing. That's amazing. So it's very basic ideas, but couched in this weird-ass calculus stuff. So I know I'm like, if you add these two up, you get the whole sum. There's nothing crazy. You're like, yeah, I know that, but I don't know this shit. But that's exactly what this thing says. Okay. That's good. That's funny. I'm so happy. Yay.